So in this video, I'm going to do an example of vector decomposition. If you don't have a calculator that you're comfortable with using the trigonometric functions on, you might want to open MATLAB online. That's what I'm going to do my computations in. And in addition, earlier this week when we posted part 2 of the engineering math lecture, on slide 6, there was the SOH-CATOA formulas, which were formulas that related the functions of the angles inside a triangle to the ratio of the lengths of the sides. So if that will be helpful, feel free to pull that up, but know that I will go through in detail and write any formula that we need. So we're given a vector A. It has a magnitude of 2 and an angle of 135 degrees. For the first thing we want to do, we want to sketch it with its tail at the origin, like we typically do. Then we want to drop perpendiculars in order to show it kind of written as the sum of a vector purely along the x-axis or the horizontal axis and purely along the y or vertical axis. And then we want to write it in Cartesian form. Another word for Cartesian form is rectangular form. So I'm just going to type that in there before I forget it, because I think I used rectangular more in the lecture than Cartesian. So let's kind of knock this out. What are we given? We're told that the magnitude of this vector is 2 and its angle is 135 degrees. So I'm just going to write that down to make sure I don't forget. And step 1, what I want to do is actually sketch that in the XY plane. So we talked about in the last example video how you actually sketch this. Remember that since all of the direction conventions are defined as angles which are positive, measured as counterclockwise rotation from the x-axis, first get the angle right, basically. So a positive 135 degrees will be from the x-axis, counterclockwise rotation of 135 degrees. And hopefully you remember from the last video that we did that 135 degrees, you can kind of break it down into 2 parts. 90, which takes you to the y-axis, and an additional 45, which will take you halfway between the y and the negative x-axis. So this vector is going to be along a line that is at a kind of 45-degree angle in the second quadrant, and it's going to be of length 2. So that is what the vector looks like, and that is our part 1. So part 2, what we were asked to do is to actually show it written as a sum of vectors in the horizontal and vertical direction. And here's always the way that you do that. Go to the actual tip of your vector A and then drop a vertical perpendicular line to the horizontal axis. So just draw it straight down. Then what you need to do is just ask yourself, which way do the vector heads need to be arranged in order to add up to A? So how could I get a vector that looks like A? Well, in order to get a vector that looks like A, I need to go to the left and then I need to go up. So I'm just going to draw little heads on these vectors, and it's going to be hard to see. I'm sorry about that. Maybe you can kind of take it out of the coordinate system and just zoom it up, but you could call this vector AY and you could call this vector AX. But what you're basically showing is very similar to the last video. You're able to write the vector as the sum of these 2 vectors. But the difference is, in the last video, you were given the 2 vectors you were adding and you were asked to draw the resultant. In this video, you were given the resultant and you've shown that you can decompose it, that AX plus AY equals A. So that's the big idea behind decomposition, showing that you can write it as the sum of 2 vectors, not only any 2 vectors, but vectors that are aligned along the horizontal and vertical direction. Now, why would you want to do it? The key reason that you want to do that is that will make this a 90-degree, this will make this a right triangle because that angle will be 90 degrees. So what I'm going to do, so this is kind of step 1 and 2. So for step 3, I'm actually going to step back. And rather than showing all the vectors, I'm just going to draw this as a triangle. And what do I know about this triangle? Well, I know that that angle is 90 degrees. In addition, I know that this entire angle from the positive x-axis to this line here is 135 degrees. So what's that mean about this interior angle? Well, you know that if you go from the positive x-axis to the negative x-axis, these 2 angles, if you call this alpha, for example, alpha plus 135, those 2 have to sum to 180 degrees. So what that means is that the interior angle within that triangle is just 45 degrees. So let me just draw that up again just to make it a little bit easier to see. So we have a triangle where we actually know every angle inside, right? Because we know that this is 90 because we dropped this in a perpendicular fashion. If this is 45, then that has to be 45 because the 3 angles in the triangle have to sum to 180 degrees. In addition, we know the side length corresponding to the hypotenuse. That is just the magnitude of that vector, or 2. And what we want to find is this side length and that side length. So I'll call this AY and I'll call this AX. So the question is, how am I ever going to find those? Well, I know an angle and I know the hypotenuse. What I'm going to need to do is use those trig functions or SOHCAHTOA that we spoke of earlier. So if I think about this angle and the two sides that I want to find relative to the side that I know, notice that, for example, AY is opposite of this 45-degree angle versus the side that we know is the hypotenuse. So if you look at the acronym SOHCAHTOA, ask yourself, for which of these trig functions, sine, cosine, or tangent, do I know the opposite side? Or sorry, does it involve the opposite side that I want to find versus the hypotenuse, which I know? So which of these three, 1, 2, 3, has opposite and hypotenuse in it? It's this one. It's SO. And what this really means is that the sine of whatever angle we're kind of using to define the opposite side length, so in this case 45 degrees, that number, it's just a number that we can get from a calculator, is equal to the ratio of the opposite side length, AY, divided by the hypotenuse, which is 2. That's great, but the key thing is this is just a number. Maybe it's one that you have memorized from some class you've taken previously, but what you really want to solve for is AY. And the way that you're going to solve for AY in terms of getting it by itself, since it's divided by 2, you want to multiply both sides by 2. And what that tells you is that you can compute the side length AY as 2 times the sine of 45 degrees. And I'm going to leave that there for now because we're going to go back and compute both that we need in terms of rounding them to decimal points in MATLAB a little bit later on after I get the expression for AX. So relative to this 45-degree angle, notice that AX is adjacent. So we need to find the adjacent angle, and we know the hypotenuse. So what we're going to use here is the actual cosine function. So cos 45, by definition, is the ratio of the adjacent side length, AX, divided by the hypotenuse, or 2. So using similar type of manipulation of algebra, I can find that AX, the side length that I want to find, is just 2 times cos of 45. Now, if you've taken trigonometry and you've seen this beforehand, you know that these two quantities are actually equal, which is not surprising because a 45-degree angle means for each step left, take one step up. So these lengths are going to actually be the same. But just showing you how you actually enter those in MATLAB, since you're going to be entering an angle in degrees, you need to use the COSD function and the SIN D function. So AY, and I can define it as a variable if I want, just in case I want to use it later. I'm going to define the variable AY as 2 times the sine of 45 degrees. And that comes out to be a decimal. In fact, you probably remember that the sine of 45 is 1 over the square root of 2, or 0.707 rounded. It's an irrational number. So we're just going to have to pick how to round these two, and I'll always give you that on your exams or homework. I'm going to choose to round it to 3 decimal points. So that's going to be 1.414. And notice if I use my up key in order, since the next command will look quite similar, rather than defining AY, I'll define AX. That's going to require me to use the cosine function, and that will come out to be 1.414. Now, if you've seen this before, you know where this is going. Those are the lengths of this actual triangle. That's just a physical length, 1.414, 1.414. But we actually want to show how we can write, I'm going to zoom out a little bit, the vector A is the sum of these two vectors. Well, remember that the basis vectors that we have, the I hat and j hat, or sorry, we call them the x hat and y hat. X hat and y hat live on the positive axes. So plus x and plus y. So even though these are lengths, when you actually think about writing them as vectors, and I'm going to redraw my coordinate system, what you're going to need to do is take, like, for example, to make this vector AX, since it has to go to the left, it has to be 1.414 long. However, in addition, you're going to need to take x hat, since it usually goes along plus x, and you're going to need to rotate it by 180 degrees. So that's why, like, when you actually draw the vector that you need to go along this horizontal base, it's actually going to be that distance, 1.414, times negative x hat. And the reason is because x hat lies along the positive direction. So this will be minus 1.414 x hat. So oftentimes you will hear this minus 1.414 called the x component of A. So whenever the x component is negative, that means that vector is somewhere in the second or third quadrant. However, for the y component, if you think about that, it also has that length of 1.414. However, since we need the vector ay to go in the vertical direction, which is consistent with the direction of y hat. I'm not going to need to add that negative sign. So I'm just going to, sorry, I should have wrote that a little bit farther away. 1.414 y hat, that is the vector that goes up. So we know that if we add these two vectors together, we get a. So basically what we're saying here is that we can write a as minus 1.414 x hat plus 1.414 y hat. So this is actually called the rectangular form of the vector a, because you've written it as its x component, which is used to weight the basis vector along the horizontal direction. And then you're adding to that a vector that consists of the basis vector in the vertical direction, y hat, weighted by the y component. So you can write this in a bunch of different ways. If you remember back to that slide where I showed you earlier, you can just write the x component first and then the y component, separate them by commas and put them into these kind of triangular brackets. You could use I hat and j hat or so on, but that is the process for actually doing the decomposition. But if you notice, that was a little bit clunky because we had to be careful to remember to adjust the x component with a -1, because we knew that just kind of seeing the geometry, we needed it to go to the left. A key takeaway that I want you to have from this is, as long as you use an angle that's defined with our standard convention, meaning it's measured from the positive x-axis, you can always just use these formulas. And I'll show you why this works. If you want to find, and these are going to be on the next lecture, usually when I teach this, I show someone how to do it using actual trigonometry, and then I show them the shortcut formulas. But the x component of a vector is always just the magnitude times the cosine of the angle. And the y component is always the magnitude times the sine of the angle. But the key is, this angle must be standard, meaning that it has to be measured from the positive x-axis with a counterclockwise convention. So if you repeat this, and rather than typing using 45, if you use 2 cos of 135 and 2 sine of 135, notice that going back to MATLAB here, the x component, when we used 45, remember we had to adjust it with the negative manually. If instead I put 2 times cos of 135, notice that that negative will automatically show up. And if I do the sine that way, I get the same answer. So if you don't want to think about having to do manual sign adjustments when you do vector decomposition, just always use those formulas that I showed you there, but make sure that your angles are referenced from the positive x-axis with a counterclockwise convention. However, if you're going into engineering, particularly mechanical or civil, and you need to be able, I think it's valuable to make sure that you can do the actual decompositions by hand and show the triangles and whatnot. That is incredibly important, particularly when you take your basic structures classes, so like statics, when you're analyzing trusses, moving on to strength of materials and so on. It is a tool that will be very, very beneficial to you rather than just always relying on the formulas.